Hello, and welcome. Find yourself somewhere comfortable tonight. Maybe you're already nestled beneath warm blankets, or perhaps you're settling into your favorite chair as the day winds down around you. Wherever you are, take a moment to let your shoulders drop, to release the tension you've been carrying. Tonight, we're embarking on a journey together, one that will carry us to the very edge of time itself, to contemplate something both unsettling and strangely beautiful: the end of everything. The universe will end. This isn't pessimism or doomsaying, but simply what physics tells us. Everything that has a beginning must have an ending, and our cosmos, born in the unimaginable fire of the Big Bang some 13.8 billion years ago, will one day reach its final chapter. But how? That's the question that keeps cosmologists awake at night, even as it might gently lull you towards sleep. Tonight, we'll explore the leading scenarios that science has proposed, each one stranger and more profound than the last. So take another deep breath. Let the worries of your day begin to dissolve. We're going to travel trillions upon trillions of years into the future, to witness events so vast and slow that they dwarf human comprehension. Along the way, you might find your eyelids growing heavy. That's perfectly fine. Let this be a journey that carries you toward rest, even as we explore the ultimate end of all things. Are you ready? Then let us begin. The weight of endings. There's something deeply human about wondering how things will end. We write stories with final chapters. We watch the sun set knowing it will rise again. We contemplate our own mortality in quiet moments. But the end of the universe, that's a different scale of ending altogether. It's an ending so distant, so incomprehensibly far in the future, that it shouldn't matter to us at all, and yet here we are, thinking about it. For most of human history, people believed the universe was eternal, unchanging, infinite in both time and space. The stars wheeled overhead in their eternal dance, seemingly permanent fixtures in the night sky, even when ancient philosophers wondered about the nature of reality. Few of them imagined that reality itself might have an expiration date. The cosmos simply was, had always been, would always. That comfortable certainty began to crumble in the early 20th century. In 1915, Albert Einstein published his general theory of relativity, a revolutionary framework that described gravity not as a force but as the curvature of space-time itself. When he applied his equations to the universe as a whole, Einstein made a disturbing discovery. His equations didn't allow for a static, unchanging universe. The cosmos, according to his own theory, had to be either expanding or contracting. It couldn't simply sit still. Einstein, like most people of his time, believed in an eternal, static universe. So he did something that would haunt him for the rest of his life. He added a term to his equations, a mathematical fudge factor he called the cosmological constant, specifically designed to hold the universe still, to keep it from either expanding or collapsing. It was a band-aid, a patch job, something that made the math work but didn't emerge naturally from the physics. Einstein would later call it his greatest blunder, because the universe, as it turned out, was not static at all. In the 1920s and 30s, an astronomer named Edwin Hubble, using the massive telescope at Mount Wilson Observatory in California, made careful observations of distant galaxies. What he discovered changed everything. The galaxies weren't standing still. They were moving away from us, and the farther away they were, the faster they seemed to be receding. Space itself was expanding, carrying the galaxies along with it like raisins in rising bread dough. This wasn't just movement through space. This was the expansion of space itself, a stretching of the very fabric of reality. And if space was expanding now, that meant it must have been smaller in the past. Wind a clock back far enough, and you arrive at a moment when all of space was compressed into a single point, infinitely dense and infinitely hot. The Big Bang. The universe had a beginning, and if it had a beginning, well, it seemed reasonable to ask whether it might also have an end. For decades after Hubble's discovery, cosmologists debated the universe's ultimate fate. The question seemed to hinge on a simple balance. On one side you had the expansion, the outward momentum left over from the Big Bang, pushing everything apart. On the other side you had gravity, the attractive force of all the matter in the universe, trying to pull everything back together. Which force would win? If there was enough matter, enough mass, enough gravitational pull, then eventually the expansion would slow down, stop, and revert. The universe would begin to contract, falling back in on itself, heading toward what physicists called the Big Crunch, a mirror image of the Big Bang. All the galaxies would rush back together, space would compress, temperatures would skyrocket, and everything would be crushed out of existence in a final cataclysmic collapse. But if there wasn't enough matter, if gravity was too weak to overcome that initial expansive push, then the universe would keep expanding forever. Galaxies would drift farther and farther apart, stars would burn out one by one, the cosmos would grow cold and dark and empty, fading into what became known as the Big Freeze, or the heat death, a slow, gradual decline into maximum entropy, maximum disorder, a state where nothing interesting could ever happen again. For most of the late 20th century, measurements suggested the universe was hovering right on the edge, almost perfectly balanced between these two fates. The density of matter seemed to be almost exactly at the critical value, the knife edge between collapse and eternal expansion. It was a delicate balance, a cosmic coincidence that no one could quite explain. Then came 1998, and everything changed again. Two independent teams of astronomers, studying distant supernova explosions, made an observation that shocked the scientific world. They expected to measure how much the universe's expansion was slowing down. Instead, they discovered something no one had predicted. The expansion wasn't slowing down at all, it was speeding up. The universe's expansion was accelerating. This made no sense. Nothing in the known physics could explain it. Gravity should slow expansion down, not speed it up. It was like throwing a ball in the air and watching it accelerate upward instead of falling back down. Something was pushing the galaxies apart, something that worked against gravity, something that became stronger as the universe got bigger. Scientists had no idea what it was, so they gave it a placeholder name: dark energy. Dark energy, whatever it is, makes up about 68% of the total energy content of the universe. It's everywhere, permeating all of space, and its nature remains one of the deepest mysteries in physics. But its existence has profound implications for the fate of the cosmos. If dark energy remains constant, the universe will expand forever, accelerating all the while, heading toward a cold, lonely end. But if dark energy changes over time, if it grows stronger or weaker, or behaves in unexpected ways, then all bets are off. The universe's fate becomes uncertain again. And here's where things get interesting. In April 2024, the Dark Energy Spectroscopic Instrument, or DESI, a powerful telescope perched on Kitt Peak in Arizona, released preliminary findings that sent ripples through the cosmology community. Their data, based on measurements of how the universe has expanded over the past 11 billion years, suggests something unexpected. Dark energy might not be constant after all. It might be evolving, changing, potentially even weakening over time. If this finding holds up under further scrutiny, it would revolutionize our understanding of the universe's fate. A weakening dark energy could mean the universe won't expand forever. Gravity might eventually win after all, leading to a big crunch scenario, or dark energy might strengthen instead, leading to something even more dramatic. The measurements are still uncertain, the debate ongoing, but suddenly the question of how the universe ends has become less settled than it seemed just a few years ago. So tonight, as you settle in and let these words wash over you, we're going to explore the major scenarios that physics has proposed. Each one is supported by mathematics, by observation, by our best understanding of how the cosmos works. Each one offers a different vision of the ultimate, and each one in its own way is both terrifying and beautiful, a reminder of the vast scales on which the universe operates, scales that make our brief human lives seem like the flicker of a match in an endless night. Are you comfortable? Good. Let's begin our journey through the possible ends of every. The Big Freeze, a slow fade to darkness. Imagine standing outside on a clear winter night, far from city lights. The stars spread above you in countless thousands, the Milky Way a river of light flowing across the darkness. It's beautiful, peaceful, eternal, except it's not eternal at all. Every star you see is burning through its fuel, converting hydrogen into helium through nuclear fusion in its core, slowly but inexorably consuming the very thing that keeps it shining. And one day, each of those stars will run out of fuel and go dark. This is the essence of the Big Freeze scenario, also known as heat death. It's the most widely accepted ending among cosmologists today, the fate that current observations suggest is most likely. It's not a dramatic end, not a sudden catastrophe. It's a gradual decline, a slow fading, the universe running down like a clock whose spring is unwinding, tick by tick, until finally it stops. The Big Freeze is based on a fundamental principle of physics called the second law of thermodynamics. This law states that in any closed system, entropy always increases over time. Entropy is often described as disorder, though that's not quite right. It's better understood as the spreading out of energy, the tendency of concentrated useful energy to become dispersed, diffuse, unusable. A cup of hot coffee left on a table will cool to room temperature. The thermal energy doesn't disappear, but it spreads out, becomes evenly distributed. And once it's spread out evenly, you can't get it back. You can't unmix the cream from your coffee. You can't unscramble an egg. Energy flows in one direction, from concentrated to dispersed, from useful to useless, from order to disorder. If the universe is a closed system, and most cosmologists believe it is, then the same principle applies on a cosmic scale. All the concentrated energy in the universe, all the stars burning in their galaxies, all the black holes spinning in space, all the matter clumped into planets and asteroids and clouds of gas, all of it is slowly, inexorably spreading out, cooling down, heading toward a state of maximum entropy where everything is uniformly distributed and nothing interesting can happen anymore. This process takes an unimaginably long time. We're not talking about millions or billions of years. We're talking about time scales that make the current age of the universe seem like an eye blink. But let's try to wrap our minds around it anyway. Let's follow the timeline of the Big Freeze, step by step, era by era, until we reach the final darkness. We start now, or rather, we start about 6 billion years ago. That's when dark energy, this mysterious repulsive force, became the dominant factor in the universe's expansion. Before that, the universe was still expanding, but gravity was slowing it down. Matter was the dominant force. Galaxies were still being drawn together by their mutual gravitational attraction, forming clusters and superclusters, great cosmic webs of structure, spanning hundreds of millions of light years. But 6 billion years ago, the universe had expanded enough that dark energy took over. Space itself started pushing things apart faster than gravity could pull them together. The expansion began to accelerate, and from that point on, any galaxy that wasn't already gravitationally bound to our local neighborhood began to slip away, receding faster and faster, eventually moving so quickly that its light can never reach us. Fast forward to about 100 billion years from now. By this point, the accelerating expansion will have carried distant galaxies beyond our cosmic horizon. An astronomer looking up at the night sky from Earth, assuming Earth still exists and there are still astronomers, would see a profoundly different view than we see tonight. The billions of galaxies that currently fill deep space images would have vanished, receded beyond the reach of light itself. The sky would show only our local group of galaxies, the Milky Way, Andromeda, and a few dozen smaller companions. Everything else would be gone, lost beyond an impassable horizon, isolated from us forever. And the process wouldn't stop there. About 1 trillion years from now, give or take a few hundred billion, the last stars in our galaxy will flicker out. You see, star formation requires clouds of gas, hydrogen and helium, that can collapse under their own gravity and ignite nuclear fusion in their cores. But there's only so much gas available. Once it's all been incorporated into stars, once the clouds have been depleted, no new stars can form. The universe will have used up its stellar fuel. The stars that already exist will keep burning for a while, some of them for trillions of years, especially the small red dwarfs that burn their fuel so slowly they can last longer than the current age of the universe. But eventually, even they will exhaust their hydrogen, fuse their helium into heavier elements, and finally cool into dim, dark remnants. White dwarfs, the dense cores of sun-like stars, will slowly radiate away their heat until they become black dwarfs, cold and dark and dead. Neutron stars, the crushed remnants of massive stars, will likewise cool over unthinkable spans of time, and the galaxies themselves will go dark, filled with dead stars, brown dwarfs that never quite ignited, and the scattered debris of planetary systems long since disrupted. But even in this dark era, the universe won't be completely empty. There will still be black holes, those regions of space-time where gravity is so intense that nothing can escape, not even light. Black holes will, in fact, become the dominant inhabitants of the cosmos. As stars die and stellar remnants drift through space, they'll occasionally collide, merge, or get too close to a black hole and be consumed. The black holes themselves will merge when they encounter each other, growing larger and larger, accumulating mass over each. Our own Milky Way galaxy has a supermassive black hole at its center, weighing in at about 4 million times the mass of our Sun. In the distant future, as stars die and the galaxy continues its slow dynamical evolution, more and more matter will eventually find its way into that central black hole. The same process will occur in other galaxies. The universe will become a collection of black holes of various sizes, drifting through an ever-expanding void, separated by distances that grow larger with each passing eon. And here's where things get truly strange. Black holes aren't actually permanent. In 1974, physicist Stephen Hawking made a remarkable discovery using quantum mechanics and general relativity. He showed that black holes emit radiation, a faint thermal glow that arises from quantum effects near the event horizon. This radiation, now called Hawking radiation, causes black holes to slowly lose mass over time. They evaporate. The process is extraordinarily slow. A black hole with the mass of our Sun would take about 10 to the 67th power years to evaporate completely. That's a 1 followed by 67 zeros, a number so large it's almost meaningless. The current age of the universe is only about 10 to the 10th power years, a 1 followed by 10 zeros. We're talking about timescales that are 10 billion times longer than the universe has currently existed. But here's the thing about eternity. No matter how long something takes, given infinite time, it will happen. And in the big freeze scenario, time stretches on forever. So even though it takes an absurdly long time, eventually every black hole in the universe will evaporate into radiation. A solar mass black hole will take 10 to the 67th year. A supermassive black hole like the one at the center of our galaxy will take even longer. Some of the largest black holes in the universe, weighing in at tens of billions of solar masses, won't evaporate until approximately 10 to the 100th power years have passed. Imagine that timescale for a moment. It's so vast that you can't really imagine it. The number of particles in the entire observable universe is only about 10 to the 80th power. The age of the universe in Planck times, the smallest meaningful unit of time in physics, is only about 10 to the 60 power. We're talking about a timescale so long that it makes the age of the universe seem instantaneous in comparison. Let me try to give you some perspective on these numbers, impossible as that task is. If you started counting at the moment of the Big Bang, counting one number per second, you still wouldn't have reached 10 to the 100th power. Not even close. You could count for the entire current age of the universe, and then do it again and again, and again, billions upon billions of times, and you would still be nowhere near that number. It's a time scale that defies human comprehension, that exists beyond the reach of analogy or metaphor. During this black hole era, the universe will be almost unrecognizable compared to what we see today. There will be no stars, their light long since extinguished. No planets, their orbits long since disrupted by gravitational perturbation. No galaxies as organized structures, just scattered remnants drifting through ever-expanding space. The dominant objects will be black holes of various sizes, slowly evaporating through Hawking radiation, and a sparse scattering of other stellar remnants. Brown dwarfs that never quite manage to become stars, white dwarfs that have cooled to the point where they emit no visible light, becoming black dwarfs, essentially just spheres of dense matter drifting through the void. Neutron stars, those incredibly dense remnants of massive stars, also cooled and dark. Between these objects, vast distances, unimaginable distances. The expansion of space, driven by dark energy, will have carried objects so far apart that what we now call the observable universe, a sphere roughly 93 billion light-years across, will seem tiny in comparison. Galaxies that were once neighbors will be separated by distances measured not in millions of light-years, but in billions, trillions, incomprehensible spans that light itself, traveling at its constant cosmic speed limit, could never cross in any meaningful time. And the temperature of space itself will continue to drop. Right now, the cosmic microwave background radiation has a temperature of about 2.7 Kelvin, just a few degrees above absolute zero. This is the cooled remnant of the intense radiation that filled the universe shortly after the Big Bang. As space expands, This radiation gets stretched to longer and longer wavelengths, cooling as it goes. In the black hole era, it will have cooled to a tiny fraction of a Kelvin, 1/10 of a degree, 1/100th, 1,000th, approaching but never quite reaching absolute zero, that theoretical temperature at which all thermal motion ceases. In such a cold, dark universe, quantum effects would become the only source of activity. Space, according to quantum mechanics, is never truly empty, never truly still. It's filled with quantum fluctuations, tiny temporary violations of energy conservation that are allowed by Heisenberg's uncertainty principle. Virtual particles pop into existence in pairs. A particle and its antiparticle exist for a brief moment and then annihilate each other and disappear. These fluctuations are happening everywhere, all the time, even in the deepest vacuum of space. In a warm, dense universe like ours, these quantum fluctuations are insignificant, drowned out by the much larger effects of normal matter and radiation. But in the cold, empty universe of the far future, they become the dominant phenomenon. And over truly vast time scales, these fluctuations can occasionally produce something macroscopic. But wait, we're still not done, because even after all the black holes have evaporated, the universe will continue to expand, and as it expands, it will continue to cool. The cosmic microwave background radiation, that faint afterglow of the Big Bang that currently fills space with a temperature of about 3 Kelvin, just 3 degrees above absolute zero, will continue to cool as space stretches. Its temperature will drop toward 1 Kelvin, then 1/10 of a Kelvin, then 100th, approaching but never quite reaching absolute zero. In this unimaginably distant future, the universe will be almost completely dark and cold. Almost. There will still be stray particles, photons of light stretched to wavelengths larger than galaxies, electrons and positrons drifting alone through the void. These particles will be separated by distances so vast that they will almost never interact. An electron might drift for 10 to the 106th power years before encountering another particle. And yet, even in this darkness, something curious might happen. According to quantum mechanics, empty space isn't truly empty. It seethes with virtual particles, quantum fluctuations that pop in and out of existence on timescales so brief we can barely measure them. But given enough time, given absurdly, ridiculously, incomprehensibly long periods of time, these fluctuations might produce something macroscopic. Physicists have calculated that, very, very occasionally, purely by random chance, these quantum fluctuations might produce a fully formed brain, complete with memories and thoughts, that exists for a brief moment before dissipating back into the void. These hypothetical entities are called Boltzmann brains, named after the physicist Ludwig Boltzmann, who first grappled with the statistical nature of thermodynamics. In the vast emptiness of the heat death, Boltzmann brains might be the only conscious observers, flickering in and out of existence, separated by time scales that make the evaporation of black holes look quick. It's a strange, unsettling thought, but it illustrates just how empty and dark the universe becomes in the Big Freeze scenario. This is maximum entropy, maximum disorder. All the stars have burned out, all the black holes have evaporated, all the energy has been spread so thin, so diffuse, so evenly distributed, that nothing interesting can happen. No stars can form, no life can exist, no thoughts can be thought, except perhaps for those brief random Boltzmann fluctuations. The universe doesn't end in any dramatic sense, it just fades, gradually,
asymptotically approaching a state of perfect equilibrium, and in that equilibrium, time itself becomes meaningless. When nothing changes, when no processes occur, when no events mark the passage of moments, what does time even mean? The universe reaches a state that is, for all practical purposes, dead. But here's the thing. This scenario assumes that dark energy remains constant, that it behaves like Einstein's cosmological constant, an unchanging property of space itself. If dark energy is truly constant, then the Big Freeze is almost certainly our fate. Current observations support this picture. The universe's expansion is accelerating at a steady rate, showing no signs of changing. Yet those dizzy results from 2024 hint at something different. They suggest tentatively that dark energy might be weakening over time. If that's true, if dark energy isn't constant, then the future might unfold differently. The expansion might slow down. It might even and that leads us to our next scenario, one that's fallen out of favor in recent decades, but might be making a comeback. But we'll get to that. For now, let the image of the Big Freeze settle in your mind. A slow fade to darkness, a gradual running down, the universe cooling, expanding, emptying, until finally, there's nothing left but scattered particles in an endless void. It's a peaceful ending, in its way. Gentle, quiet, like drifting off to sleep and never waking up. The universe doesn't die violently. It just stops being interesting. And perhaps, in the grand scheme of things, that's not the worst way for a cosmos to end. Rest now. Let the darkness gather around you. We have other scenarios to explore, but for now, just breathe and let yourself settle into the quiet. The Big Freeze is a long, slow goodbye, and sometimes a slow goodbye is a kind gift. Are you comfortable? Good. Let's begin our journey through the possible ends of everything.
The big RIP, a violent unraveling. Wake up, but only just a little. We need to shift gears now, to contemplate something much more violent, much more sudden. If the Big Freeze is a gentle fade to black, the Big Rip is the universe tearing itself apart in a cosmic catastrophe that destroys everything, right down to the subatomic level. It's a scenario that sounds like science fiction, but it emerges from serious physics, from the equations that describe dark energy and cosmic expansion. Remember dark energy, that mysterious force causing the universe's expansion to accelerate. We don't know what it is. It might be a property of space itself, a cosmological constant as Einstein imagined, but it might be something more dynamic, something that changes over time, something that could grow stronger and stronger without limit. Physicists call this hypothetical form of dark energy phantom energy. Unlike normal matter, or radiation, or even the cosmological constant, phantom energy has a peculiar property. Its density increases as the universe expands. Think about that for a moment. Normally, when you expand a container of gas, the gas becomes less dense. Spread matter out over a larger volume, and you have less matter per unit volume. That's basic physics. But phantom energy doesn't work that way. As space expands, phantom energy doesn't dilute. Instead, it intensifies. There's more of it per unit volume after expansion than before. This violates several fundamental assumptions in physics, which is why many physicists are skeptical that phantom energy actually exists. But the equations allow for it, and if it exists, the consequences are dramatic. To understand phantom energy, we need to talk about something called the equation of state parameter, usually denoted by the letter W. This parameter describes the relationship between a substance's pressure and its energy density. For normal matter, like the atoms in your body or the gas in a star, W equals 0. For radiation like light, W equals 1/3. For a cosmological constant, Einstein's version of dark energy, W equals -1. That negative value is crucial. It means dark energy has negative pressure, a kind of cosmic tension that pushes space apart rather than pulling it together. But W equals -1 is a special case, a boundary. If W is greater than -1, say -0.9, the dark energy is called quintessence, and while it accelerates the universe's expansion, it does so in a controlled way that doesn't lead to catastrophe. The big freeze scenario still applies, but if W is less than -1, if it's -1.1 or -1.5 or even more negative, then you have phantom energy. And phantom energy leads to the Big Rip. Here's how it works. Phantom energy's density increases as the universe expands. More space means more dark energy, which means stronger repulsive force, which means faster expansion, which means even more space, which means even more dark energy. It's a runaway feedback loop, an exponentially accelerating process that grows more violent with every passing moment. In a phantom energy universe, the expansion doesn't just speed up. It speeds up faster and faster until it becomes infinite in finite time. The Hubble parameter, which measures the rate of expansion, diverges to infinity, and when that happens, everything in the universe gets ripped apart by tidal forces. Let's walk through the timeline of the Big Rip, step by step, to see how it unfolds. The specific timing depends on how negative W is, how strong the phantom energy is. For the sake of illustration, let's use the example that physicist Robert Caldwell and his colleagues calculated back in 2003, assuming W equals -1.5, a moderately strong phantom energy. In their calculation, starting from today, the Big Rip would occur in about 22 billion years. That might sound like a long time, and it is, plenty of time for stars to burn and galaxies to evolve. But compared to the Big Freeze, which plays out over timescales of 10 to the 100th power years, the Big Rip is shockingly quick. The universe exists for only about twice its current age before being destroyed completely. The first sign of trouble appears about 1 billion years before the Big Rip, when galaxy clusters start to come apart. Galaxy clusters are massive structures, collections of hundreds or thousands of galaxies held together by their mutual gravity. They're some of the largest gravitationally bound objects in the universe. But as phantom energy's density increases, the repulsive force it generates begins to overwhelm the gravitational attraction holding these clusters together. Galaxies that were orbiting each other for billions of years suddenly find themselves being pushed apart faster than gravity can hold them. The clusters disintegrate, their member galaxies flung outward into the expanding void. An observer in one of these galaxies would see neighboring galaxies accelerating away, receding faster and faster until they disappear beyond the horizon. The cosmic web of structure, that magnificent network of filaments and clusters spanning billions of light years, begins to fray and now we jump forward to about 60 million years before the Big Rip. This is when individual galaxies themselves start to come apart. The Milky Way, our home galaxy, a beautiful spiral containing hundreds of billions of stars, held together by gravity for over 10 billion years, begins to disintegrate, The outer spiral arms, where gravity's hold is weakest, start to pull away first. Stars that have been orbiting the galactic center for eons suddenly find themselves being torn from their orbits by the ever-strengthening phantom energy. The galaxy doesn't explode exactly. It's more like it dissolves, its stars scattered into the void like dandelion seeds blown by an impossible wind. An observer on a planet orbiting one of these stars would see the night sky transform. The Milky Way, that river of light arching across the darkness, would fade and fragment. Other stars would appear to accelerate away in all directions. Within a relatively short time, astronomically speaking, each star would find itself alone in space, isolated from its former companion. 3 months before the Big Rip, the phantom energy has grown so strong that it begins to overcome the gravity holding solar systems together. Earth's orbit around the Sun, stable for billions of years, starts to expand. Slowly at first, then fast, the Earth spirals outward, away from the Sun that has warmed it since its formation. The other planets do the same, each following its own outward trajectory. The solar system, that orderly arrangement of planets and moons and asteroids and comets, falls apart. An observer on Earth, if there are any observers left, would notice the Sun shrinking in the sky. Its warmth would fade. The Earth would grow cold, its oceans freezing solid, its atmosphere eventually freezing and falling to the ground as snow. But the cold would be the least of Earth's problems, because worse is coming. About 30 minutes before the Big Rip, the phantom energy becomes strong enough to overcome the gravitational and electromagnetic forces holding planets together. Earth itself, this solid ball of rock and metal that has existed for over 4.5 billion years, begins to come apart. The process starts at the surface. Rocks and mountains and continents start to lift away from the planet, torn off by tidal force. The oceans, no longer held in their basins, boil off into space. The atmosphere escapes, and then the solid Earth itself fragments, breaking into ever smaller pieces. It's not an explosion. It's more like watching something dissolve in acid. But instead of acid, it's the fabric of space itself, expanding so violently that the forces holding matter together can't compete. The pieces of Earth drift apart, each one continuing to fragment further. What was once a planet becomes a cloud of debris, and then the debris itself begins to break down. 15 minutes before the Big Rip, the Sun disintegrates. Stars are held together by a delicate balance between gravity trying to crush them and the outward pressure of nuclear fusion in their cores. When phantom energy overwhelms gravity, that balance collapses. The Sun, our Sun, the star that has shone steadily for billions of years, comes apart. Its outer layers are torn away first, dispersing into space, then the inner layers, finally even the core, that incredibly dense region where hydrogen is being fused into helium, fragments and scatters. And now we're in the final just fractions of a second before the Big Rip. Phantom energy has become so intense that it overcomes even the strong nuclear force, the most powerful force in nature, the force that holds atomic nuclei together. Atoms themselves are torn apart. An atom consists of a nucleus of protons and neutrons, surrounded by electrons. The electrons, orbiting the nucleus, are ripped away first. Then the nucleus itself disintegrates, protons and neutrons torn from each other. But even that's not the end. In the final infinitesimal fraction of a second, about 10 to the negative 19th power seconds before the Big Rip, the phantom energy overcomes the forces holding protons and neutrons together.
These particles aren't fundamental, they're made of quarks, even smaller particles held together by the strong force via particles called gluons. In normal circumstances, you can't separate quarks. If you try to pull two quarks apart, the energy you put in creates new quarks instead. It's like trying to cut a string in half and finding you now have two strings. But in the Big Rip, the phantom energy is so overwhelmingly strong that even this fails. Quarks are torn from each other. Protons and neutrons, the building blocks of atomic nuclei, the particles that make up all the ordinary matter in the universe, disintegrate. And then, in the final instant, space-time itself becomes so violently curved, so severely distorted by the infinite expansion rate, that it ceases to have meaning. The universe ends not with a whimper, but with a tear, a ripping apart of the very fabric of reality, and then, nothing, or perhaps something we can't even describe, because the laws of physics as we understand them no longer apply. The Big Rip is a genuine singularity, a point where our equations break down and our understanding fails. It's the end of everything, an end so total and complete that even the atoms and subatomic particles that once composed you and me and the stars and the galaxies are obliterated. It's a terrifying scenario, more visceral than the slow fade of the Big Freeze, more immediate, more violent. The universe doesn't gently decline into darkness. It's destroyed, torn to shreds in a cosmic catastrophe that spares nothing. But here's the crucial question. Is the Big Rip actually going to happen? Current observations suggest probably not. Measurements of dark energy's equation of state parameter, that crucial blue value, indicate it's very close to -1. The cosmological constant, the latest data from supernova observations, from the cosmic microwave background, from large-scale structure surveys, all point to W being somewhere around -1, perhaps -1.03, give or take. If W equals exactly -1, the Big Rip can't happen. The expansion accelerates forever, leading to the Big Freeze, but it never becomes infinite in finite time. And even if W is slightly less than -1, say -1.05, the Big Rip is pushed so far into the future, hundreds of billions or trillions of years, that it becomes less relevant. Though with the uncertainties in our measurements still fairly large, we can't completely rule out a Big Rip scenario. That DESI data from 2024, suggesting that dark energy might be evolving, adds another wrinkle. If dark energy is getting weaker over time, that pushes us away from phantom energy, away from the Big Rip, toward either the Big Freeze, or even a Big Crunch. But if it's getting stronger, if W is decreasing, becoming more negative over time, then the Big Rip could be in our future after all. So we wait, we observe, we build better telescopes and conduct more precise surveys. We measure the universe's expansion rate at different points in its history, trying to pin down exactly how dark energy behaves. And in the meantime, we can rest a bit easier knowing that while the Big Rip is possible, it doesn't appear to be probable based on current evidence. But the mathematics is there, the physics allows for it, and that alone is worth contemplating. The universe could, in principle, tear itself apart so violently that even the fundamental particles of matter are destroyed. It's a reminder of just how strange and extreme the cosmos can be, how the laws of physics permit outcomes that stretch our imagination to its limits and beyond. Take a deep breath now. Let the tension of the Big Rip dissolve. It's just one possibility, one branch of the many forking paths the universe might take. Rest here for a moment. Feel the solidity of the world around you. The atoms of your body held together by forces that for now and for the foreseeable future are vastly stronger than any cosmic expansion. You're safe. The big rip, if it comes at all, is in the unimaginably distant future. Sleep, and let those fears drift away like mist in the morning sun.
The big crunch, collapse, and rebirth. Let's shift now to something different. Something that for decades was considered the most likely fate of the universe before dark energy changed everything. The big crunch. It's almost poetic in its symmetry. If the universe began in the Big Bang, an explosion outward from an infinitely dense point, why shouldn't it end in the big crunch, an implosion inward back to an infinitely dense point? The big crunch scenario emerges naturally from general relativity if you assume the universe contains enough matter and no dark energy, or if dark energy reverses sign and becomes attractive rather than repulsive. In this scenario, the expansion that began 13.8 billion years ago would eventually slow down, stop, and reverse. Gravity would win. The universe would begin to contract, slowly at first, then faster and faster, until everything that exists comes crashing back together in a final cataclysm of heat and light. For most of the 20th century, this seemed like a real possibility. Before the discovery of dark energy, the question of the universe's fate hinged on a single parameter called omega, the ratio of the universe's actual density to its critical density. If omega is greater than 1, if there's enough matter, the universe is closed and will eventually recollapse in a big crunch. If omega is less than 1, the universe is open and will expand forever, leading to a big freeze. And if omega equals exactly 1, the universe is flat and will expand forever, but at an ever-slowing rate. Measurements in the 1980s and 90s suggested omega was close to 1, tantalizingly close, but the uncertainty was large enough that people weren't sure which side of the critical value we fell on. The discovery of dark energy in 1998 seemed to settle the question. The universe would expand forever. The big crunch was off the table. But that DESI data has reopened the question. If dark energy is weakening, as those measurements hint, then at some point in the future, gravity might become the dominant force again. The expansion could slow down, stop, and reverse, leading to a big crunch, after all just delayed by billions of years compared to what earlier models predicted. So let's explore what the big crunch would actually look like. Let's imagine a universe where, for whatever reason, the expansion eventually reverses. Maybe dark energy fades away. Maybe it changes sign, becoming repulsive. Maybe there's more dark matter than we've measured, and its gravitational pull is stronger than we thought. The specifics don't matter as much as the outcome. The universe begins to contract. For a very long time, nothing seems different. The contraction begins so slowly that it's imperceptible. Galaxies continue on their courses. Stars are born and die. Planets orbit their suns. Life, wherever it exists, goes about its business. The only hint that something has changed would come from careful measurements of distant galaxies. Instead of receding as they have been for billions of years, they would start to move close. Their light would be blue-shifted rather than red-shifted, compressed toward shorter wavelengths as they approach rather than stretched toward longer wavelengths as they recede. But as time goes on, millions of years, tens of millions, hundreds of millions, the contraction accelerates. Gravity is inexorable. Once it starts pulling things together, it doesn't stop. It gets stronger as things get closer. Galaxies that were moving apart now move together. Galaxy clusters that were expanding now contract. The entire cosmic web, that grand structure of filaments and voids begins to collapse in on itself. About 1 billion years before the Big Crunch, assuming a similar timeline to the Big Rip, but running in reverse, the effects would become more dramatic. Galaxies that were separated by millions of light years start to collide. And when galaxies collide, it's a spectacular event. Despite containing billions of stars each, galaxies are mostly empty space. So when two galaxies merge, the stars themselves rarely collide. Instead, they pass through each other like two swarms of bees interpenetrating. But the gas clouds within the galaxies do collide, slamming together at speeds of thousands of kilometers per second. These collisions compress the gas, triggering intense bursts of star formation. Massive stars form rapidly, burn through their fuel in just millions of years, and explode as supernovae. The merged galaxies light up with brilliant blue stars and the fierce radiation from newly formed stellar nurseries. It's beautiful, in a violent sort of way. The universe becomes brighter, more active, more dynamic, as gravity pulls structures together. But it doesn't stop there. As the contraction continues, galaxies don't just merge, they start to overlap, to compress. The spaces between stars shrink, and as the universe gets smaller, it also gets hotter. This is the flip side of cosmic expansion. When the universe expands, it cools, like a gas expanding from a pressurized tank. When it contracts, it heats up, like a gas being compressed in a piston. The cosmic microwave background radiation, that faint afterglow of the Big Bang, currently at a chilly 3 Kelvin, begins to warm. As the universe contracts, the wavelengths of these photons get compressed, blue shifted toward higher energies. The temperature rises, 10 Kelvin, 100 Kelvin, 1000 Kelvin. The universe, which has been cooling for nearly 14 billion years, reverses course and starts heating up again. About 60 million years before the Big Crunch, individual galaxies can no longer maintain their structure. The spaces between them have shrunk so much that tidal forces from neighboring galaxies start to tear them apart. Stars are ripped from their orbits. The beautifully organized spiral and elliptical shapes that characterize galaxies dissolve into chaos. The universe becomes a hot, dense soup of stars and gas, all falling inward together. The temperature continues to rise. At some point, maybe 10 million years before the end, the cosmic microwave background becomes hotter than the surfaces of stars, which have been shining by emitting light into the cooler space around them, find themselves bathed in radiation hotter than they are. They begin to heat up from the outside. Their surfaces blaze with energy. Nuclear fusion rates in their cores skyrocket as temperatures climb. Massive stars explode prematurely. Smaller stars puff up into giants, their outer layers stripped away by the intense radiation pressure. And still the contraction continues. A million years before the Big Crunch, the temperature has climbed into the millions of degrees. Atoms can't hold together. The electrons are stripped away by the intense thermal radiation, leaving behind naked nuclei. The universe becomes a plasma, like the interior of a star, but spread across all of space. Matter and energy intermingle. Photons carry enormous energies, smashing into particles, creating new particles from pure energy, in reactions that mimic the conditions in the first moments after the Big Bang. 3 months before the end, the temperature is in the billions of degrees. Even atomic nuclei start to break apart, dissociating into individual protons and neutrons. The fundamental building blocks of matter are laid bare. And then, in the final moments,
As the universe contracts to a size smaller than a galaxy, smaller than a solar system, smaller than a planet, the temperature climbs beyond anything we can easily describe. Trillions of degrees, quadrillion. The energy density becomes so high that space-time itself begins to distort and warp. In the final fractions of a second, quantum effects become important. The smooth fabric of space-time, which has served as the stage for all cosmic events since the Big Bang, becomes choppy, foamy, uncertain. Gravity, which has been the dominant force driving the contraction, merges with the other fundamental forces in ways we don't fully understand. The laws of physics, as we know them, break down. Our equations fail. We approach a singularity, a point of infinite density and temperature, where the mathematics gives nonsensical answers and our understanding runs out. And then, the big, all the matter and energy in the universe, all the galaxies and stars and planets, and atoms and particles, compressed into a single point, a reversal of the Big Bang. Everything that exists, crushed out of existence. Time itself comes to an end, or at least, the time of this universe. What happens next, if anything happens next, is pure speculation. Some cosmologists have suggested that the Big Crunch might trigger a new Big Bang, a cosmic rebound. The universe bounces, it contracts to some minimum size, perhaps not quite zero but something very small, at the Planck scale where quantum gravity effects dominate, and then it bounces back, expanding again in a new Big Bang. This leads to a cyclic model of the cosmos, an eternal series of expansions and contractions, Big Bangs and Big Crunches, each cycle lasting hundreds of billions of years. In this model, our universe might be just one cycle in an infinite series. Before our Big Bang, there might have been a previous universe that contracted and bounced, and before that, another one, and before that, another. An eternal cycle, with no beginning and no end, just an endless rhythm of expansion and contraction, like the breathing of some cosmic being. It's an appealing idea philosophically. It avoids the uncomfortable question of what came before the Big Bang, by saying there's always something before, stretching back infinitely into the past. But it raises its own question. Does each cycle start with the same conditions, producing the same universe over and over? Or are the conditions slightly different each time, producing an infinite variety of universes, each one unique? And what mechanism causes the bounce? What prevents the contraction from going all the way to a singularity? Physicists working on loop quantum gravity, a candidate theory of quantum gravity, have suggested that quantum effects might indeed prevent a true singularity. At extremely small scales, near the Planck length, space-time might become discrete, granular, like pixels on a screen rather than a smooth continuum, and this granularity might act like a spring, resisting further compression, causing the universe to bounce back before reaching infinite density. But this is all highly speculative. We don't have a complete theory of quantum gravity yet. We don't know what happens at energies and densities beyond our ability to take. The Big Crunch and the possible bounce that might follow are extrapolations far beyond what we can observe or experiment with. Moreover, current observations suggest the Big Crunch isn't our likely fate. The universe is accelerating, not decelerate, unless dark energy does something unexpected, unless those desired hints of evolution turn out to be real and significant. We're headed for eternal expansion, not contraction. The Big Crunch remains a possibility, but it's no longer the favored scenario. Still, it's worth contemplating. The symmetry of it appeals to our aesthetic sense. The universe begins with a bang and ends with a crunch, a closed loop, a complete story with a definite beginning and a definite end. And if there's a bounce, if the universe is reborn after its death, then in a sense nothing is really lost. The universe dies but rises again, phoenix-like from its own ashes. It's a less lonely ending than the big freeze, less violent than the big rip. It's almost comforting, in a strange way. Not a fading away, not a tearing apart, but a gathering together, a return to the source, a closing of the circle, from unity to diversity and back to unity again. All that is scattered is gathered up, all that was separated is reunited. The universe comes home. Rest here for a moment. Imagine the warmth of that gathering, even as it becomes too hot to bear. Imagine the light, growing brighter and brighter as everything draws together. In the big crunch, the universe doesn't go gentle into that good night. It goes out in a blaze of glory, a final tremendous flash of light and heat, and then perhaps rebirth, another chance, another universe, another beginning. Let that thought settle. We'll move on soon to even stranger scenarios, but for now, just breathe in and out, like the breathing of a cyclic universe, expansion and contraction, life and death and life again. It's beautiful, in its way. Sleep on that thought for now. We have more journeys ahead.
Vacuum decay. Reality's phase transition. Now we come to perhaps the strangest scenario of all. One that sounds more like science fiction than science fact, but which emerges from serious considerations of quantum field theory and particle physics. This is vacuum decay, sometimes called false vacuum decay, and it's based on an unsettling possibility that the universe we live in might not be stable, not in the sense that it's expanding or contracting, but in a more fundamental sense. The very fabric of reality, the quantum fields that underlie all matter and energy, might be in a temporary, metastable state. And if they are, they could suddenly transition to a more stable state, rewriting the laws of physics as we know them, and destroying everything in the process. To understand this scenario, we need to talk about energy landscapes and quantum fields. Imagine a ball sitting in a shallow valley on a hillside. It's stable there, in the sense that it's not rolling anywhere, but it's not in the lowest possible position. The valley bottom is below, at the base of the hill. The ball is in what physicists call a local minimum, a stable position that's not the absolute lowest energy state. If you gave the ball a big enough push, it could roll over the ridge and down to the true valley bottom, the global minimum, the lowest energy state. This is the essence of the false vacuum problem. The quantum fields that permeate the universe, including the famous Higgs field that gives particles their mass, might be sitting in a local minimum rather than a global minimum. They're stable, but not perfectly stable. They're in what's called a metastable or false vacuum state. And just like that ball on the hillside, if they're given the right kind of push, or if quantum tunneling allows them to spontaneously jump over the energy barrier, they could transition to the true vacuum state, the lowest possible energy level. The Higgs field is particularly relevant here. When physicists discovered the Higgs boson at the Large Hadron Collider in 2012, they were able to measure its mass with increasing precision, and when they plugged that mass into their equations, along with the mass of the top quark, another fundamental particle, they found something unsettling. Based on the standard model of particle physics, our current best theory of matter and forces, the Higgs field appears to be in a metastable state. The calculations suggest that at very high energies, far higher than anything we can produce in particle accelerators, but energies that would have existed in the early universe or in extreme astrophysical events, the Higgs potential changes shape. It develops another valley, deeper than the one we're currently in. This means our vacuum, the state of lowest energy that we experience every day, might not be the absolute lowest energy state. There might be a lower state, a true vacuum, that our universe hasn't fallen into yet. The key word is yet. A metastable state can last for a very long time. Think of a supercooled liquid, water-cooled below its freezing point, but still remaining liquid, because it hasn't found a nucleation site to start forming ice crystals. It's stable until something disturbs it, and then it freezes almost instantly. The false vacuum is similar. It could persist for billions of years, trillions of years, even longer, but it's not perfectly stable. There's always a small probability that it could decay. The decay process would begin with quantum tunneling. In quantum mechanics, particles can do things that would be impossible in classical physics, like passing through barriers they don't have enough energy to climb over. They tunnel through. The same principle applies to field. Even though our universe is sitting in a false vacuum valley, there's a tiny probability that a small region of space could spontaneously tunnel through the energy barrier to the true vacuum state. This would create a bubble. Imagine a small sphere of space, perhaps subatomic in size, initially, where the quantum fields have jumped to their lower energy state. This bubble would be surrounded by a wall, a thin shell where the fields transition from the false vacuum outside to the true vacuum inside. And here's the critical part. This bubble would expand. The true vacuum has lower energy than the false vacuum. That difference in energy gets released at the bubble wall, driving its expansion. The bubble grows, spreading outward at nearly the speed of light, converting false vacuum to true vacuum as it goes. And once it starts, there's no stopping it. The bubble expands until it has consumed everything, until the entire universe has transitioned to the new vacuum state. What would it be like inside the bubble? Almost certainly, it would be incompatible with life as we know it. The laws of physics depend on the properties of the vacuum, the quantum field values that fill empty space. In the true vacuum, these values would be different. Particles might have different masses. The fundamental forces might have different strength. The very structure of atoms might be altered or impossible. Imagine a universe where electrons are too heavy to orbit protons, or where the electromagnetic force is so weak that atoms can't form at all. Chemistry as we know it wouldn't work. Stars couldn't form or couldn't burn. Planets couldn't exist. Life, at least carbon-based life like us, would be impossible. The interior of the bubble would be a sterile alien place, operating under rules we wouldn't recognize, and the transition would be instantaneous. From our perspective, the bubble wall moves at nearly the speed of light. We wouldn't see it coming. Light from the approaching wall would reach us at the same moment the wall itself arrives. One moment, you're living in the universe you know, with its familiar laws of physics. The next moment, less than a heartbeat later, you're not living at all, because the atoms that compose you have been fundamentally altered or destroyed by the change in vacuum state. Some calculations suggest that the bubble wall itself would carry enormous energy, enough to incinerate anything it encountered. Others suggest that the transition might be more subtle, simply changing the properties of matter without releasing much energy. But either way, the result is the same. Everything inside the bubble is transformed, and that transformation is not compatible with the continued existence of stars, planets, or life. Perhaps even more unsettling, the transition might not stop with destroying matter. Some physicists, including Sidney Coleman and Frank DeLucia in a famous paper from 1980, calculated that a bubble of true vacuum might undergo immediate gravitational collapse. The energy released at the bubble wall could be so enormous that it distorts space-time, creating a black hole that swallows everything inside the bubble. The universe doesn't just change, it collapses into a singularity. Now, before you panic, let's put this in perspective. First, the probability of vacuum decay happening at any given moment is extraordinarily small. Based on current calculations, the lifetime of our metastable vacuum is much, much longer than the current age of the universe. We're talking about timescales of 10 to the 100 power years or more, longer than it would take for all black holes to evaporate in the Big Freeze scenario. The odds of vacuum decay occurring in the next billion years, or even the next trillion years, are vanishingly tiny. Second, we're not even certain that our vacuum is metastable. The calculations depend on extrapolating the standard model to extremely high energies, far beyond what we can test experimentally. There might be new physics at those energies, new particles or forces that we haven't discovered yet, that stabilize the Higgs field and prevent vacuum decay entirely. Many physicists expect that the standard model will be replaced or modified by a more complete theory before we reach those energies, a theory that might make the vacuum perfectly stable. Third, even if our vacuum is metastable, it has survived for 13.8 billion years already. The early universe was extremely hot and energetic, with particles colliding at energies far higher than anything in the universe today. If those conditions didn't trigger vacuum decay, it suggests that the barrier protecting us is quite high. The universe appears to have made it through the most dangerous period and is now coasting in a relatively stable configuration. But still, the possibility exists. Somewhere in the universe, at some random point in space, a quantum fluctuation could nucleate a bubble of true vacuum. It would begin to expand, consuming everything in its path, propagating across the cosmos at nearly the speed of light. We would have no warning. We couldn't escape. The bubble would arrive before we knew it was coming, and in an instant everything we know would be gone, replaced by something utterly alien, or by nothing at all. It's the ultimate cosmic catastrophe, not a slow fade like the Big Freeze, not a violent unraveling like the Big Rip, not even a hot collapse like the Big Crunch. Vacuum decay is instant, total, and absolute. One moment the universe exists, the next moment it's gone, or at least so transformed that it might as well be gone. All structure destroyed, all life extinguished, all history erased. A clean slate, as if the universe had been reset to factory settings. There's a grim poetry to it. The universe ends not because it runs out of energy or expands too far or collapses back on itself, but because it discovers a better way to exist, a lower energy state, and in making that transition, it destroys everything built in the old configuration. It's like a computer program discovering a bug in its code and crashing to the desktop. A fundamental flaw in the structure of reality, hidden for billions of years, suddenly made manifest. But here's a thought. If vacuum decay does occur, if the bubble wall sweeps across the cosmos at light speed, erasing everything in its path, consider this. The transition is so fast that no one would suffer. There would be no time for fear, no time for pain. You would cease to exist in literally less than a heartbeat,
passing from being to non-being in an instant too brief to measure. In a sense, it's the gentlest of the catastrophic scenarios. Not a slow death, not a violent death, but an instantaneous transition from existence to non-existence, like a switch being flipped off. And who knows, maybe the new vacuum, the true vacuum, could support its own forms of structure, its own kinds of complexity, perhaps even its own forms of life, radically different from anything we could imagine but no less valid. Maybe vacuum decay isn't the end. Maybe it's just a transformation. The universe shedding one skin for another, dying in one form to be reborn in another. We can't know. We can only speculate. So rest easy. The probability is infinitesimally small. The universe has survived for nearly 14 billion years. It will likely survive for trillions more. And if vacuum decay does occur, it will be so quick you won't even know it happened. No suffering, no fear, just a clean, instant transition. In the grand scheme of cosmic endings, there are far worse fates. Let that thought comfort you. Close your eye, breathe. The universe is stable enough for now, and now is all that matters. Sleep well, and know that the quantum fields underlying reality are, for the moment, holding steady.
The Big Bounce. Quantum resurrection. Let's end our tour of cosmic catastrophes on a slightly more hopeful note. What if the universe doesn't really end at all? What if the apparent endpoints we've been discussing, the singularities where our equations break down and time seems to stop, are actually transition points, portals to something new? This is the idea behind the Big Bounce scenario, a model that suggests the universe is cyclic, eternal, endlessly dying and being reborn in a cosmic rhythm that has no beginning and no end. We touched on this idea briefly when discussing the Big Crunch. If the universe contracts back to a point, maybe it doesn't end there. Maybe it bounces, rebounding into a new expansion, a new Big Bang, a new universe with new galaxies and stars and planets. But the Big Bounce concept goes deeper than. It's based on attempts to merge quantum mechanics with general relativity, to create a theory of quantum gravity that can describe what happens at the Planck scale, those extreme conditions where space-time itself becomes quantum and uncertain. One of the leading approaches to quantum gravity is called loop quantum gravity. It's a framework that suggests space-time isn't smooth and continuous at the smallest scales, but is instead made up of discrete chunks, tiny loops of space and time, that interweave to create the fabric of reality we experience. Think of it like the pixels on a screen. From a distance, an image looks smooth and continuous, but zoom in far enough, and you see the individual pixels, the discrete units that compose the image. Loop quantum gravity predicts that when matter is compressed to extremely high densities approaching what's called the Planck density, quantum effects kick in that prevent further compression. Space-time can't be squeezed beyond a certain. It resists, like a spring being compressed, and when the pressure becomes too great, it bounces back. This means singularities, those points of infinite density that plague our classical understanding of black holes and the Big Bang, might not exist at all. They might be artifacts of our incomplete theories, problems that go away when we properly account for quantum effects. If loop quantum gravity is correct, and that's still a big if, then the Big Bang wasn't a moment of creation from nothing. It was a bounce, a rebound from a previous contracting phase. Before our universe expanded, there was another universe that contracted. It collapsed down to the Planck scale, couldn't compress any further because of quantum resistance, and then bounced back. beginning the expansion we observe today. What would that previous universe have been like? We can't know for sure. Loop quantum gravity suggests that information might be preserved through the bounce, that some properties of the previous universe could be encoded in the initial conditions of our universe. But it's also possible that the bounce acts like a cosmic reset button, erasing most or all details of what came before, leaving us with no way to probe the prior cycle. This leads to a model of the universe that's radically different from the classical Big Bang picture. Instead of the universe having a definite beginning 13.8 billion years ago, it has existed forever, cycling through endless expansions and contractions. Each cycle might last hundreds of billions of years, maybe longer. Our cycle is just the current iteration, one of infinitely many. And if our universe is heading toward a big crunch, if dark energy reverses or weakens enough for gravity to win, then we'll eventually contract, compress to the Planck scale, and bounce again, beginning a new cycle. The universe will be reborn, fresh and new, expanding into a new era of galaxies and stars. It's a phoenix cosmology, death and resurrection, woven into the very fabric of cosmic evolution. There's something deeply appealing about this idea. It solves the problem of the initial singularity, the uncomfortable question of what came before the Big Bang, or what caused it. The answer is simple: there was no first moment. The universe has always existed, bouncing eternally. It also provides a kind of cosmic optimism. Even if our cycle ends, even if everything we know is destroyed in a big crunch, it's not truly the end. Something new will emerge, a new universe, a new chance for structure and complexity and perhaps even life. But the big bounce faces challenge. For one thing, we don't have a complete tested theory of quantum gravity. Loop quantum gravity is one approach among several, and it's not yet developed to the point where it makes specific testable predictions that we can verify experimentally. It might be the right path, or it might be a dead end. We simply don't know yet. Moreover, for the universe to bounce, it needs to contract first, and current observations, the accelerating expansion driven by dark energy, suggest that's not our unless dark energy does something unexpected, we're headed for eternal expansion and the big freeze, not contraction, and a potential bounce. The big bounce might be mathematically possible, but it doesn't seem to be physically likely given what we know about our universe. Still, the idea persists and evolves. Some cosmologists have proposed variations on the big bounce that don't require a full contraction. Maybe each cycle begins and ends differently. Maybe there are multiple universes, a multiverse, where some universes bounce and others don't. Maybe quantum effects could cause a bounce even in an expanding universe under certain exotic conditions. The point is, the big bounce represents a different way of thinking about cosmic ending. It reframes them not as final terminations, but as transitions, as moments of transformation from one state to another. The universe doesn't die. It changes. It evolves. It continues endlessly, in a dance of expansion and contraction, creation and destruction, that has no beginning and no end. And perhaps that's the most comforting thought of all. Not that the universe will last forever in some static sense, but that even when it seems to end, it's only ending one chapter to begin another. The story doesn't stop. It just turns the page, starts a new paragraph, continues in a new direction. Everything changes, but change itself is eternal. So as you lie here, settling deeper into rest, consider the big bounce. Imagine the universe breathing, expanding and contracting like lungs, like waves on a shore, an eternal rhythm that persists through all time. Our lives are brief sparks in this vast cycle, but the cycle itself goes on. There's a peace in a knowledge that even endings aren't final, that transformation is the way of things, that what seems like death might just be a doorway to rebirth. Rest now. Let your breathing sync with that cosmic rhythm, in and out, expansion and contraction, being and become. The big bounce whispers that nothing is truly lost, only transformed, only changed, only reborn in new forms. Sleep on that. Let it carry you gently into dreams, into that nightly little death and resurrection we all experience. That reminder that endings and beginnings are always intertwined, always dancing together, always part of the same eternal story. Dark energy's mystery. We keep coming back to dark energy, don't we? It haunts every scenario we've discussed. The big freeze depends on dark energy remaining constant. The big rip requires it to strengthen. The big crunch needs it to weaken or revert. Even vacuum decay and the big bounce touch on the fundamental nature of the vacuum, which dark energy is intimately connected to. Dark energy is the wild card, the unknown factor, the X in the equation of cosmic fate. Take a moment to appreciate just how strange this situation. For thousands of years, humans looked up at the night sky and saw what they thought was the sum total of reality. Stars, planets, the moon, the sun. These were the constituents of the universe, or so it seemed. Then as our instruments improved, we discovered there was more. Distant galaxies, billions of them, scattered through space. Nebulae where stars are born, black holes where they die. The cosmic microwave background, that faint whisper of the Big Bang itself. But even with all these discoveries, we thought we understood the basic composition of the universe. It was made of matter, the stuff of atoms and molecules, protons and neutrons and electrons. There was radiation too, light and other forms of electromagnetic waves, and there was space and time, woven together into the fabric of space-time, as Einstein showed us. Matter, radiation and geometry. Those were the ingredients of the cosmos. Then came the late 20th century, and everything changed. First, in the 1970s and 80s, astronomers noticed something odd about the way galaxies rotate. When you measure how fast stars orbit around the center of a galaxy, you can use that information to calculate how much mass the galaxy contains. The stars closer to the center should orbit faster than those farther out, just like planets in our solar system, where Mercury zips around the sun much faster than distant Neptune. But that's not what astronomers observed. Instead, they found that stars at the outer edges of galaxies were moving just as fast as stars closer to the center, sometimes even faster. This made no sense based on the visible matter in the galaxies. There wasn't enough mass to account for these high rotation speeds. Either the laws of gravity were wrong, which seemed unlikely given how well they worked everywhere else, or there was additional mass in the galaxies that we couldn't see. This led to the hypothesis of dark matter, invisible material that doesn't emit or absorb light, but does exert gravitational influence. Further observations confirmed it. Galaxy clusters held together by more gravity than their visible matter could provide. Gravitational lensing, where light from distant galaxies is bent by the gravity of foreground clusters, showing more mass than we could account for with stars and gas. All the evidence pointed to the same conclusion. About 85% of the matter in the universe is dark matter, something we can't see directly, something that doesn't interact with light, something whose nature remains mysterious. That was strange, but at least dark matter behaved like matter. It clumped together.
It formed structures through gravitational attraction. It followed the rules we expected, even if we didn't know what it was made of. It was a mystery, but a comprehensible one. We could imagine solutions, candidates for what dark matter might be, exotic particles left over from the Big Bang, primordial black holes, axions or neutralinos, or sterile neutrinos. We had ideas, even if we couldn't yet test them. Then came 1998, and the discovery of dark energy, and suddenly the universe became even stranger. At least dark matter was just matter, albeit invisible matter. Dark energy is something else entirely. It doesn't clump. It's smoothly distributed throughout all of space. It doesn't attract things together like gravity. It pushes things apart, acting like anti-gravity, causing the expansion of space itself to accelerate. And unlike dark matter, which makes up about 27% of the universe's total energy content, dark energy is the dominant component, making up about 68%. When you add it all up, the stuff we understand, the ordinary matter made of atoms, the material that composes stars and planets and people, makes up only about 5% of the universe. Everything we can see, everything we can touch, everything we're made of, is just a small fraction of what exists. The other 95% is dark, invisible, mysterious. And the frustrating thing, we still don't know what it is. Not real. We've given it a name, measured its effects, observed how it makes the universe's expansion accelerate, but we don't understand its fundamental nature. We don't know why it exists, how it works, or what will happen to it in the future. It's one of the deepest mysteries in all of physics. The simplest explanation is that dark energy is Einstein's cosmological constant, a property of empty space itself. According to quantum field theory, empty space isn't really empty. It's filled with virtual particles that pop in and out of existence on incredibly brief timescales. These quantum fluctuations should contribute to the energy of the vacuum, and that vacuum energy should act like a cosmological constant, causing space to expand. The problem is, when you try to calculate how much vacuum energy there should be based on quantum field theory, you get an answer that's wrong by a factor of 10 to the 120th power. That's not a typo. The prediction is off by 120 orders of magnitude, making it arguably the worst prediction in the history of physics. Clearly something is deeply wrong with our understanding, but we don't know what. So cosmologists have proposed alternative. Maybe dark energy isn't a constant at all, but a dynamical field, something that changes over time and space. They call this quintessence, after the fifth element of ancient philosophy. Quintessence would be a new kind of field permeating the universe, distinct from the electromagnetic field or the Higgs field or any of the other fields we know about. Its energy density and pressure could evolve as the universe expands, leading to different fates than a simple cosmological constant would produce. If quintessence exists, and its energy is decreasing over time, that would explain the dizzy results suggesting dark energy is weakening. It would also mean the universe's accelerated expansion might slow down in the future, potentially even stopping and reversing, if quintessence continues to decline. On the other hand, if quintessence's energy is increasing, we could be heading toward a big rip, with the expansion accelerating faster and faster, until space-time itself tears apart. The key parameter, as we've mentioned, is the equation of state parameter W, the ratio of dark energy's pressure to its density. A cosmological constant has W equal to -1, exactly. Quintessence can have W anywhere from -1 up to -1/3. And phantom energy, the stuff that causes a big rip, has W less than -1. By measuring W with increasing precision and seeing how it changes over time, if it changes at all, Cosmologists can narrow down what dark energy is and what it will do. And that's what projects like DISY are all about. They observe thousands of galaxies, measuring their distances and velocities with incredible precision, mapping out the expansion history of the universe over billions of years. They look at the cosmic microwave background, the afterglow of the Big Bang, searching for patterns that reveal the influence of dark energy on the universe's growth. They study supernova explosions, using them as cosmic yardsticks to measure distances and expansion rate. All this data gets fed into sophisticated computer models that try to extract the properties of dark energy. What's its density? How does it change over time? What's the value of W? And slowly, painstakingly, the uncertainties shrink. We get a clearer picture of what dark energy is doing, even if we don't yet understand why. Those 2024 DISY results, suggesting that dark energy might be evolving, are preliminary. They're based on early data, and more observations are needed to confirm or refute the find. But if it holds up, if dark energy really is changing, it would be a revolution in cosmology. It would rule out the simple cosmological constant model and push us toward more exotic scenarios, quintessence or phantom energy, or something even stranger that we haven't thought of yet. And here's the thing, the universe doesn't care what we think. It's going to do what it's going to do, following the laws of physics, whether we understand them or not. Our models, our scenarios, our calculations, they're all just attempts to describe reality, not prescriptions for how reality must behave. Nature is under no obligation to make sense to us, to fit into neat categories, to follow the rules we've discovered so far. So when we talk about dark energy, we're really talking about our ignorance. We're saying there's something out there, something making up more than 2/3 of the universe's energy content, and we have no idea what it is. That's humbling. It reminds us how much we still have to learn, how vast the unknowns are compared to the knowns, how the universe continually surprises us. And perhaps that's a good thing. If we knew everything, if we had all the answers, there would be nothing left to discover, no mysteries to solve, no sense of wonder at the universe's strangeness. Dark energy, in all its mystery, keeps us humble and curious. It's a reminder that no matter how much we learn, there's always more to understand, always deeper questions to ask, always new horizons to explore. So as you settle into sleep, think about dark energy, this invisible, mysterious force that fills the universe, that drives galaxies apart, that might determine the ultimate fate of all that exists. We don't know what it is. We can't see it or touch it or interact with it in any way except through its gravitational effect. And yet it's there, everywhere, influencing the cosmos on the largest scales imaginable. It's a reminder that the universe is far stranger than we often realize, that reality hides secrets, layers of complexity that we're only beginning to unravel.
And that our journey of understanding is far from over. We live in an age of discovery, where fundamental questions about the nature and fate of the universe are still open, still being actively investigated, still capable of surprising us. That's exciting. It means the story isn't finished. The final chapter hasn't been written. We're still in the middle of the plot, and we don't yet know how it ends. And maybe that's how it should be. Maybe the journey is more important than the destination. Maybe asking the questions is more valuable than having all the answers. Rest, let the mystery wash over you. Dark energy, dark matter, dark secrets of the cosmos. They're out there, waiting to be understood, patient as the stars, enduring as the universe itself. And tomorrow, scientists will wake up and continue the search, piece by piece, building our understanding of this strange and beautiful reality we inhabit. That tonight, in the darkness behind your eyes, you can simply wonder, simply marvel, simply let the mystery, the human perspective. We've journeyed far tonight, you and I. We've watched the universe fade in the big freeze, tear apart in the big rip, collapse in the big crunch, transform in vacuum decay, and bounce in quantum resurrection. We've contemplated endings on timescales so vast they make the age of the Earth seem like a moment. Timescales that stretch into deep time, into forever, into regimes where our intuition fails, and only mathematics can guide us. But now, let's come back from those distant futures, those unimaginable eons, back to the present, back to you, lying here in the darkness, breathing softly, existing in this moment. Because here's the thing, none of those cosmic endings matter to you, not really. Not in any practical sense. The big freeze, if it happens, won't occur for tens or hundreds of billions of years. The stars will shine for eons yet. Planets will orbit. Life, somewhere in the cosmos, will go on. The big rip, if it's real, is pushed so far into the future that it might as well be fictional. The big crunch requires a reversal of cosmic expansion that shows no signs of happening. Vacuum decay is extraordinarily improbable, and the big bounce, if it occurs, is so far beyond our horizon that it's purely theoretical. You will live your life. You will wake tomorrow and go about your day. You will experience joy and sorrow, success and failure, love and loss. All the beautiful complexity of being human, and none of it will be affected in the slightest by the ultimate fate of the universe. The cosmos will continue on its path, and you will continue on yours, and the two will intersect only in moments like this, when you pause to contemplate the vastness of it all. There's a certain freedom in that. The universe doesn't need you to worry about. It's going to do what it does whether you understand it or not, whether you think about it or not. You can let go of any anxiety about cosmic endings. They're not your problem. They're not anyone's problem really, because by the time they occur, if they occur, there will be no one left to be affected by them. What matters is now. This moment, this breath, the life you're living, the people you love, the work you do, the beauty you experience. In the grand scheme of things, in the trillions of years of cosmic history, your life is a brief spark. But it's your spark. It's unique. It's irreplaceable. And it matters, not because it lasts forever, but because it exists at all. Think about that for a moment. Against all odds, you exist. The universe in its vast complexity, in its intricate dance of matter and energy, has arranged itself in such a way that you are here, conscious, aware, able to contemplate your own existence and the existence of the cosmos around you. That's remarkable. It's a kind of miracle if you think about it. Not a supernatural miracle, but a natural one. The miracle of complexity arising from simplicity, of consciousness emerging from matter, of meaning existing in a universe that fundamentally is just quantum fields and space-time geometry. And you're not alone. Somewhere out there, under these same stars, other people are living their lives, experiencing their own moments of wonder and fear and joy. Perhaps on other planets, orbiting other stars, other forms of life are doing the same, thinking their own thoughts, asking their own questions. The universe, for all its vastness and eventual fate, is alive with consciousness right now, in this present moment. and that's beautiful. The endings we've discussed tonight, they're not depressing when you really think about them. They're just different chapters in a story that's almost incomprehensibly long. The universe began, it evolved, it produced stars and galaxies and planets, and eventually life. And one day it will end, or transform, or continue in ways we can't yet imagine. That's the nature of stories. They have beginnings, middles and ends. And the ending doesn't diminish the middle. It doesn't make the story meaning. If anything, the fact that it ends gives it shape, gives it structure, makes it a story at all. Your life is the same way. It has a beginning, a middle, and it will have an end. That's not tragic. That's just how it is. And the end doesn't diminish the value of the middle, the life you're living right now. If anything, the fact that your time is limited makes it more precious, more valuable, more worth experiencing fully. So instead of worrying about cosmic endings, maybe we can appreciate cosmic middle. The fact that we exist in a time when stars are shining, when galaxies are forming, when planets orbit their suns in stable configurations that allow for the existence of life. We live in the stelliferous era, the age of stars, a golden age of the universe that will last for trillions of years, but which is still just a chapter in the much longer story of cosmic evolution. And in this chapter, in this moment, you have the privilege of being aware, of looking up at the night sky and seeing those distant suns, of wondering about the nature of reality, of asking questions about how it all began and how it might end. That capacity for wonder, for curiosity, for contemplation, that's one of the most precious things in the universe. It might even be the most precious thing, because as far as we know, we're the universe's way of knowing itself, of being aware of itself, of experiencing its own existence. When you look up at the stars, you're not just you looking at them, you're the universe looking at itself. The atoms in your body were forged in the hearts of ancient stars. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of it was created in stellar furnaces billions of years ago. You are literally made of star stuff, as Carl Sagan famously said, and when you contemplate the cosmos, you're engaging in a profound act of cosmic self-reflection. So rest now. Let go of worries about endings, cosmic or personal. They'll come when they come, and in the meantime there's life to be lived, beauty to be experienced, love to be given and received. The universe will take care of itself. It's been doing so for nearly 14 billion years, and it will continue doing so long after we're gone. Your job isn't to save the universe or to worry about its fate. Your job is simply to be, to exist, to experience, to appreciate the remarkable fact that you are here at all, conscious and aware in this vast cosmos. That's enough. That's more than enough. That's everything. As you drift towards sleep now, carry with you this thought: you are part of something unimaginably vast and ancient and beautiful. The universe flows through you and around you and within you. Your consciousness is a tiny flame in the cosmic darkness, but it's a real flame, a true light, however brief. And while it burns, it matters. You matter, not because you'll last forever, but because you exist now, in this moment, fully and completely. The universe will end, one way or another, in one scenario or another, in time scales we can barely comprehend. But that's tomorrow's problem. Today's gift is existence. Today's miracle is awareness. Today's blessing is this moment, this breath, this life. Cherish it. Not because it lasts forever, but because it doesn't, because it's finite and fragile, and fleeting and beautiful precisely because of that. Sleep well, dream peacefully, and know that whatever the ultimate fate of the cosmos, you have lived, you have been aware, you have experienced wonder, and that in the end, is what truly matters. The universe gave you this gift of existence. How you use it, how you experience it, what you make of it, that's your contribution to the cosmic story. Make it a good one. But for now, rest. Tomorrow is soon enough to continue writing your chapter. Tonight, just be, just breathe, just sleep. Closing thoughts. And so we've arrived at the end of our journey, you and I. Though the universe's journey continues on, we've explored 5 major scenarios for how it all might end. The slow fade of the big freeze, the violent tearing of the big rip, the crushing collapse of the big crunch, the sudden transformation of vacuum decay, and the eternal cycle of the big bounce. Each one is grounded in physics, in mathematics, in our best understanding of how the cosmos works. Each one offers a different vision of finality or transformation. But here's what's remarkable. We don't know which one is right. Despite all our telescopes and satellites and equations, despite centuries of careful observation and brilliant theorizing, the ultimate fate of the universe remains an open question. We have clues, hints, provisional answers, but we don't have certainty, and perhaps we never will. That's not a failure of science. It's a reminder of the magnitude of the questions we're asking. We're trying to predict events trillions of years in the future, trying to understand phenomena at energy scales we can never directly probe, trying to comprehend concepts that stretch our mathematics and our imagination to their limits. It's no surprise that definitive answers elude us, but the search itself is worthwhile. Every measurement we make, every observation we conduct, every theory we develop, brings us closer to understanding the nature of reality. We may never know with absolute certainty how the universe will end, but we're getting better at narrowing down the possibilities, at constraining the scenarios, at understanding the underlying physics. And in the meantime, we have wonder. We have the capacity to imagine these vast futures, to contemplate endings beyond human scale, to think thoughts that transcend our brief existence. That capacity for wonder, for imagination, for asking questions that might never be answered, that's one of the most human things about it, and it's precious. So as you close your eyes tonight, as sleep finally claims you, carry with you this sense of wonder. The universe is vast and ancient and strange. It had a beginning. It will have an end. And in between, for this brief cosmic moment, we are here, aware, able to contemplate it all. That's a gift. An extraordinary, unlikely, beautiful gift. Before you go, I'd like to invite you to join our community here on Science Lullaby. If you've found comfort in this journey tonight, if you've enjoyed exploring these cosmic questions while drifting towards sleep, please consider subscribing to the channel. Hit that like button if this video helped you find peace, and check out our other videos for more sleep-friendly explorations of science and the cosmos. But all of that can wait. For now, just rest. Let sleep take you. Dream of stars and galaxies, of universes being born and dying, of the great cosmic dance that we're all part of, however briefly. Dream peacefully, dream deeply, and know that tomorrow, the universe will still be here, still mysterious, still beautiful, still worthy of wonder. Good night, sleep well, and thank you for sharing this journey through the end of everything. Until next time, rest easy under the stars,
And remember, whatever the universe's fate, you are here now, and that's what matters. Sweet dreams.